I would like to introduce our the next speaker, and that is Dr. Vitor Silva, who is currently Seismic Risk Coordinator at the Global Earthquake Model. He received a PhD from University of Vitor in Portugal and has led many studies in vulnerability and probabilistic seismic risk assessment in countries like Turkey, Portugal, Italy, Peru, and Colombia, and participated in several multi-European and regional projects such as SERA, Synergy, Prize. And he is responsible, within GEM, he's responsible for development of the OpenQuake engine and coordination of the risk activities in various parts of the world, including South America, Sub-Saharan Africa, United States, and Southeast Asia. And most of these projects are supported by multilateral agencies, international organizations such as SUZI-SAEE, United States Agency for International Development, etc. And he also coordinates and reviews projects for the Global Facility for Disaster Risk Reduction, and which is related with the development of global databases of risk information. And finally, he has conducted trainings regarding earthquake loss estimation in the Middle East, Central Asia, South America, and Europe. And I would also like to add that he is also a winner of the ERI's Schach Family Prize Award for Young Researchers. So it is our honor and pleasure to have Vitor here and learn about seismic risk framework of GEM and a bit of background on seismic risk as well. So please.
Thank you, Svetlana, for the introduction. Good morning, everyone. I'm very honored to be here in this room. I've been working with Svetlana for some years, but I think you outdid yourself on such a beautiful room, so I'm very happy to be here. So my idea today is just to present some of the resources, some of the data sets, some of the models which are available through the Global Earthquake Model, a little bit more at the global scale, and then we'll have a presentation from Dr. Crowley about the specifics for Europe. Let me apologize in advance that the presentation goes all the way from some very basic concepts that perhaps you know already about this, so feel free to ignore this part. But then obviously I will also go to more detailed results and models which are already publicly available. So just to give you a little bit of context, we know that we have better models every year, right? We have better seismic hazard, better tools, more information about exposure, satellite data, and vulnerability, but still we have earthquake losses continue increasing, some of them due to ground shaking, probable liquefaction, landslides, and tsunami. So despite the fact that we have better science and better scientists, the losses keep increasing. Some of the reasons because of that is, of course, we have more exposure, right? We have more value, and if you have more value, you have more losses. We have the population increasing, right? We will reach the 9 billion people in 2050, so of course it's more value. But sometimes it's also increases in the vulnerability in some countries. Certainly not here in the Balkans, but in some countries we have what we call incremental vulnerability. We have buildings which have been designed for 3 stories, and they're no longer 3 stories, now they are 5 or 4 because they keep increasing the number of stories. And also lack of maintenance, and the buildings, the vulnerability of the buildings tends to increase. In some places, of course, if you think about climate change, we also have an increase in the hazard. That's not the case for earthquakes, at least for ground shaking. But if you think about liquefaction, and in some places in the world, like for instance New Zealand, a huge portion of the losses came from liquefaction. With the rise of the sea levels, we actually should expect more events, more liquefaction phenomena. So we should also expect a slight increase in the hazard. So because of that, we have obviously an increase on the risk. A lot of the things that we can do, or some of the things that GEM has been doing, is try to produce a lot of information that can support decision makings in various measures. So for instance, this is an event that happened in Portugal. It was basically a simulation. This is why this is in Portuguese. But basically before they did all these activities, they actually ran a few scenarios, and I will talk a little bit about scenarios, just to try to understand. This was in Lisbon, trying to understand what are the places where we should expect more fatalities, casualties, are the bridges going to work, are the hospitals going to be safe? So there was a lot of risk modeling before this event took place. And some of these calculations can be done with the tools and data sets that will be presented here. Another thing is, of course, probably one of the most efficient ways of mitigating risk is the design regulations. And in places like, for instance, in Turkey, we can see that basically every time that a destructive event happened, there was an improvement on the code, there was a new release on the code. And this is quite common in many places in the world. But if you think about places like, for instance, Portugal, I'm from Portugal, by the way, where actually earthquakes are not that frequent, then we need another tool, right? We need to do probabilistic risk assessment to try to understand if the losses are high, if the risk is acceptable, and if it's not, then we have to propose modifications on the code. So all of this is usually, can be done through risk modeling. Another very basic risk reduction or transferring the risk from the private sector from the public sector to the private sector is, of course, insurance. And in a few places around the world, I will use, for instance, the case of Japan and New Zealand. Having insurance helps with the recovery. Okay, so this is also something. This type of models that we'll be talking here today, and Helen on the next presentation, is that a lot of these models can help developing either catastrophe insurance pools or updating insurance policies, which can help so people to recover. And finally, since I know there's a lot of engineers in the room, also the famous retrofitting campaigns. And a lot of what's been done out there is to do what we call the benefit cost analysis. So we know there are various retrofitting techniques that you can use. They have different costs, but they also have different performances. And by doing a lot of this analysis, it is possible for us to understand what is the most efficient retrofitting technique, but also sometimes maybe the best plan of action is actually to demolish the building and build a new one. And the case that you see here in Spanish was benefit cost analysis performed for schools in Bogota, in the capital of Colombia. And a lot of schools were retrofitted, and other schools were demolished and then rebuilt. And a lot of other exercises are now being undertaken in Dominican Republic, in Kyrgyzstan, and Uzbekistan, and also in a few countries in Europe. Finally, by doing this probabilistic risk assessment, it also allows us to understand what are the causes of human losses, casualties, and economic losses in a given country. For instance, this is actually an earthquake risk profile from the United Nations ISDR, and we can see, for instance, for the particular case, I can remember which country this is, but basically we can see what are the losses coming from, if it's from earthquakes, from storms, from tsunami, from floods. And there's a lot of things that we do on the earthquake side, which are also useful for floods and storms and tsunamis, like, for instance, the collection of the exposure information. And this is something that I know a lot of you have been helping already at Venezia in this component of SERA. Okay, so obviously we need portfolio risk analysis. I know that a lot of you, since you're engineers, you probably have work in site-specific risk assessment, so basically understanding the seismic safety of single buildings. When we expand this at the regional scale, at the national scale, we have other challenges. So for instance, the fact that we need to produce information for all this type of users, and this is a very wide range of uses, and we obviously have to adjust the models and the outcomes depending on the use. But we also have, for instance, the need for large seismic hazard models. And I can tell you that, for instance, the SHARE model that was produced previously as part of the European model, the new SERA model, they are complex models which take a lot of time to run. And of course, you could also think about national models which can be equally complex. We also have to include and consider a wide range of vulnerabilities because we have lack of data. We have a lot of uncertainty on the vulnerability. So the fact that even if you think about reinforced concrete with 4 stories built on the same year, we obviously know that not all the buildings are going to have the same vulnerability, so we have the building-to-building variability. When we derive these vulnerability functions, we also have to take into account what we call the record-to-record variability. The fact that 2 ground motion records with exactly the same, for example, peak ground acceleration, they will have different durations, different frequency contents, different spectral shapes, and because of that, we have to include this in the vulnerability model. We also have to develop exposure models, and this is probably one of the most challenging parts on the risk modeling, at least in my opinion, because there are several data sets out there, but we know they are incomplete, there's a lot of uncertainty, they are vague and ambiguous, and we have to make sure that we propagate this uncertainty properly. So obviously, we also have to take into account site amplification, which for site-specific studies might be a little bit easier because you can go there and you can do some measurements. But if you think about seismic risk analysis, for instance, for Serbia, we don't have site-specific measurements for the entire country. So we have to use proxies, we have to use simplified methodologies to account for that. And finally, if you imagine like all these uncertainties, the complexity of the hazard model, the spatial extent of the exposure model, a lot of these calculations are quite complex. And because of that, I would say maybe a decade ago, maybe 20 years ago, you would only find commercial software that would be capable of doing these calculations. But with GEM, there's been this effort to try to produce open source, publicly available tools to perform this type of calculations. I can just provide a little bit of background of the Global Earthquake Model Foundation. So it was founded actually 10 years ago, as Svetlana was mentioning. And one of the unique features of GEM is that it doesn't focus just on seismic hazard, doesn't focus just on the engineering part. It actually tries to be comprehensive and touch on the various parts which are important to support decision makers. So we'll talk a little bit about seismic hazard, about the geological phenomena, and I know we also have some people from seismic hazard modeling world. We then obviously bring exposure and physical vulnerability. We combine these three components to generate what we call the physical risk. So basically, it's just the direct losses, damage in buildings, direct economic losses, fatalities, casualties. And then we can, of course, also bring the socioeconomic vulnerability and resilience component. Okay, so basically, it's trying to take into account that in some places, due to the socioeconomic conditions, you might have an aggravator of the physical risk, or the opposite. It could be places where they do have capacity to cope with disasters, and because of that, they are expected to recover a little bit faster. So, just some of the principles. Helen, do you think I can have the water? Forgot about that. Some of the principles of GEM, so everything we do is try to be for public good. We rely on scientists, more than 200 scientists around the world, some of them in this room, in fact, to try to make sure that it's credible, that we're using state-of-the-art, or at least state-of-the-practice methodologies, data sets, and models. We try to be as collaborative as possible, and this is why we're here today. A lot of these models, they're not static. They are very dynamic, and basically they are updated almost on, I would say, every semester. These models are updated because basically there's more feedback. There's people from different parts of the world telling us, I disagree with these building classes. I think there's a better seismic asset model. I think the risk in this region is too high. So basically we always try to collect all of this input and we try to update the models based on this. And finally, something that is extremely important is to be open and transparent. Okay? So if I give you a seismic hazard model for your country and you think the hazard is too high in a particular city, it is possible for you to look inside the model and see why is the hazard too high here or too low somewhere else. And perhaps even more important, it's possible for you to change the model and rerun the calculations based on your assumptions. So in GEM, we've been working in several places around the world. You can see here just some examples of where we had basically regional and national project sites, okay, meetings like this ones, workshops, projects, regional programs, and so on. Okay, and everything revolves around these main three, let's say, resources. If I start from the top, the platform, and I will show you a few screenshots and videos of the platform. The platform is basically the website, okay? It's the website it's the open platform in which basically you can find their data, like earthquake catalogs, historical catalogs, fault information, but also access to some of the tools. You can use some of those models results in data, and you can use the modeling tools if you want to develop a new seismic asset model, if you want to develop a new vulnerability model, if you want to get some guidance about developing exposure data sets. And this is where we are on the modeling tools. Once you have produced your ingredients, the different components necessary to calculate seismic hazard and risk, then you can go to what we call the Earthquake Engine, which is basically the main tool which can be used to calculate seismic hazard and seismic risk. And after my presentation, after the coffee break, we will actually have a presentation by Vitor, which she's going to show a few calculations for Greece, if I'm not mistaken. So how is the earthquake, global earthquake model supporting structural engineers, risk modelers, CAT modeling companies, academics, and the public in general? So let's start from the basic, the assessment of earthquake hazard, starting from the very beginning. The answers we're trying to answer is where the seismic events can occur, what is the frequency of the seismic events, how much shaking should I expect, and quite recently we have also tried to address some of the secondary hazards like liquefaction and landsliding. Usually we can divide the seismic hazard in two main components. We have what we call the deterministic or earthquake scenarios, which is basically when you consider just a single event. Okay? And a lot of countries, and for instance, when you're working mostly with the public in general, it's easier for people to understand scenarios because it could be something that happened in the past, so people either still remember or there's historical records. And here we're talking about a location, a magnitude, fault geometry, and we estimate the ground shaking in the region. From that ground shaking, we calculate the losses. Okay? But as an alternative, instead of considering just that specific earthquake, I can try to consider all the possible events that happen in the country. Okay? I know that the different events have different rates of occurrences. Larger magnitudes will have lower occurrences. Lower magnitudes will be more frequent. And in that case, what we have is usually a map like this. It's what we call the Seismic Asset Map. This is usually what it's featured in design regulations. And usually the Seismic Asset Map shows for a given level of frequency, it could be a return period for 475 years. It just shows what is the expected ground shaking that will be exceeded for this return period. Okay? We will show also examples both of seismic hazard and also seismic risk following both approaches. They are both important and they have different uses. So one of the things that we did in JAM from the beginning was to basically try to collect all the different seismic hazard models that existed around the world, also to have an idea of what are the places in the world which are covered and places in the world which are not. This is actually available online. It's what we call the Hazard Wiki. It has been updated since I created this video, but the touch and feel is more or less the same. It follows a little bit like a Wikipedia page. And you can go there, you can see seismic hazard models which are available. You can see, for instance, the geometry of the seismic hazard models, details about implementation, uniform hazard spectra, hazard curves for specific cities, and you can also understand if the implementation on OpenQuake is producing the same results as the original software. Okay? Keep in mind that OpenQuake was released more or less in 2014. A lot of these seismic hazard models existed more than 10 years ago. So these seismic hazard models were created, and the results were calculated with other tools. So what we did was to grab these existing models and put everything in this tool in OpenQuake. So if you are an advanced user and indeed you are interested in grabbing the model and calculating hazard on your own, so there's all these resources, the tools. But for instance, if you do not want to go through the process of estimating all the seismic hazard, there's also the possibility of using pre-computed results. This is the OpenQuake platform, as I was mentioning before, and basically we have used a lot of these models and we have generated a seismic hazard map, seismic hazard curves, uniform hazard spectra for many places around the world. So you could go there, you can select one of the existing models. For different return periods, as I was mentioning before, it's possible then to start seeing some seismic hazard maps. Okay, this is the example, for instance, for Central America. It was a RESIS 2 project, which was released around 2010. You can load additional data, for instance, uniform hazard spectra, which is quite often used for design purposes, and in a few places around the world, a lot of these data sets were being created for the first time. And then you can basically click on the map and start seeing some of the results and also download the curves, usually in very normal formats, like for instance CSV, the comma separated values, which you can simply open in Microsoft Excel. Okay, so here you go. Then you can download all of this information. This is in the OpenQuake platform, but actually, maybe Helen will actually talk about the earthquake facility, FR. So there's also a sort of a version of this functionality, which is being developed specifically for Europe and actually have even more results than the ones that I'm showing here. So, as I was mentioning before, we have collected a lot of models around the world, and the idea or the goal for 2018, December 2018, was to have global coverage in terms of global seismic asset models. And this is the mosaic of the models that we have collected, okay? Either collected or developed from scratch. Why do we have different colors? Because basically the approach for the different parts of the world was different. In some places, we work directly with national institutions with the remit to develop these seismic asset models, okay? Like, for instance, Canada, United States, Saudi Arabia, Australia, New Zealand. And in these cases, it's national asset models. Some of these models were developed originally already in the earthquake engine, okay? And this is the models that you see here in pink. And other places, we have to develop internally some hazard models due to basically, in some cases, perhaps I can say lack of capacity, but very rare cases. But it was basically because there was no other model available, or the model was not publicly available, so an internal model had to be developed. We also have hazard models from publications. In this particular case, it's only the Indian subcontinent, which covers India, Nepal, Bangladesh, and Bhutan, that you see here. And finally, also models which were developed as part of regional programs, like, for instance, for Europe. It was the SHARE model, which was released in 2013, but there will be an update of the SHARE model within the SERA project that Dr. Colley will talk after the coffee break. I will say that none of these models are hard-coded in OpenWake, okay? So please do not think that by looking at this map that it is mandatory to use this seismic hazard model. For instance, if you want to do seismic hazard or risk calculation for your country, it's perfectly possible for you to just use your own model, your national model, further develop or improve your national model, and still use the same framework. It's not mandatory at all to use any of the data sets that we will present here. You can use your own input data sets. So finally, we have used all these different models, and we have produced a global seismic hazard map, okay? I think you've probably seen the GSHAP from 1999 map, a very famous map. The idea was to update this map, which was 20 years old, and this is a first version of that map. I can tell you that since this was released in December, this map has been already updated 2 times. And the idea is that this global map will continue being updated as there's new data and better data to be considered. So there's a lot of things that we can start doing already with this type of data set, with these global data sets. The first one is, how much are we exposed to seismic hazard? And what you see here in this curve is what is the percentage of population which are exposed to different levels of seismic hazard. So if you think about a very low seismic hazard, something like 0.05 G, okay, it's a level of shaking that humans might feel it, okay, it's perceivable, but it's probably not sufficient to cause significant damage in buildings. If you think about that, then 68% of the world population is exposed to, let's say, perceivable seismic hazard. Again, for this return period, it might not be capable of causing heavy damage in buildings, but people will feel it. And yesterday we were talking during dinner about a few earthquakes that actually people felt, but there was not that much damage. If you increase the level of ground shaking, for instance, to 0.1 G, this is usually a level of shaking that when you're designing a building, earthquakes start to be the leading criteria. One is leading the design of the building, and no longer other criteria like, for instance, snow or wind or the life loads. And in that case, obviously we should try to enforce design regulations. And now we look at 42% of the population around the world. So already 40% of the population around the world are located in places where seismic regulations should be enforced and are necessary. If you think about now very high seismic hazard, so basically seismic hazard which is capable of causing collapse of buildings or heavy damage even in buildings which were designed according to model regulations, then we have 23% of the global population. I will talk a little bit more about exposure right now. So basically on the seismic, I just talked about the seismic hazard, which was just a geological phenomena, just generating models, basically how much is the shaking on a given region. Now let's take a step further and talk a little bit about exposure. So in this case, we're trying to answer different questions. Where's the building stock? How is the building stock? How many people do we have? And how much does it cost? And obviously we can also have other questions like, for instance, a business interruption and so on. So starting from, again, something quite basic, which is, of course, we could send people into the street and they could collect building by building information. And for that purpose, there's this tool that GEM has supported in 2000. It was released in 2014, if I'm not mistaken, the Inventory Data Capture Tools. And basically, it's just an Android app you can install in your cell phone. You could go basically building by building and start collecting information. When we are collecting such information, it's quite important to make sure that we're using the same taxonomy, the same classification system. For example, this is the case for Pavia, Italy, where we come from. This is the old part of Pavia. It's 1,300 buildings, okay? And basically, in this particular exercise, we just sent 40 students into the city 2 afternoons. And the students went building by building, okay, and they collected information. As you can imagine, the background of the students was quite different. We had students which were not even engineers, and then we have engineers who have been working in design companies for some years. So very different backgrounds, but still we need to make sure that the way they are classifying the buildings is similar, okay? So basically, what we've been using, and it's something that Svetlana worked quite extensively, probably 5 years ago, was to using the same classification system, the same number of attributes to classify the buildings. I like this image very much because it's basically like you are defining the DNA of the building. So you can see a bunch of attributes like direction, the material of construction, electrical resisting system, the height of the building. This is all attributes which are quite important to define the size and vulnerability of the building. And then following these attributes, each one of these attributes has different options. Okay, for instance, for material of construction, you have masonry, concrete, steel, wood, maybe a mix between concrete and steel structures, and it's a fixed number of options, and basically the students will go in building by building and selecting some of these options. Okay, after 2 days, and this is actually something that I might actually recommend you, that you can do this. We have people from different countries, engineering students from civil engineering department, or even architects. It took 2 afternoons to basically classify downtown Pavia. On the 3rd day, we had the exposure model for the city was built, and then they ran calculations, and this was more or less within the time span of 2 weeks. So using this uniform approach to classify the buildings, we also use other sources of information. Okay? For instance, the housing census from the different countries. And this is something that's usually performed every 10 years. And in this case, it's not building by building because we know it's unfeasible for us to try to do this at the national scale. But we can rely on some national data sets, housing census, also statistical information about the commercial sector, about the industrial sector, the active population, the working force of the different countries. And by using these data sets at the national scale, it's possible for us to start collecting information country by country. And this was done country by country and building this exposure data sets. I'm obviously skipping a lot of steps because there's no time to go through the step by step, but this is something that we will talk a lot in this afternoon and in a presentation also by Vitor tomorrow about how the exposure model for SERA for Europe is being built. This is just basically some information about this global exposure model. For instance, in Southeast Asia, it was very challenging to develop this exposure model because whatever is the building typology that you can imagine, it exists in Southeast Asia. From different combinations of wood and bamboo with masonry, concrete mixed with wood. Okay, and basically this was quite challenging to do in Southeast Asia. Also in some places, like for instance in China, it was quite challenging again because there's a lot of information, very detailed information for a country, for instance, the size of China, or for instance in Japan, but there was a lot of information that has to be compiled. Because the same taxonomy was used, the same system to classify the buildings between different countries, it is actually possible for me now to compare directly the building portfolio, for instance, in China with the building portfolio in Japan, or for instance in Serbia, because the same approach is being used to classify the building stock. So in terms of all the information that can be collected and then used within the OpenQuake engine, this is just a brief list. So it's obviously the number of buildings, if you want to do some damage assessment to calculate a few scenarios. In some places around the world, instead of using the number of buildings, it's quite common to use the built-up area from the different sectors. The economic value can be defined either just for the building, okay, or you can actually divide this between the structural components of the building, the non-structural components, the contents, and also if you have some information about how much does it cost for a given enterprise to stop working, then you can also take into account, for instance, business interruption. So already trying to take into account not just the direct losses, but also the indirect losses. If you are interested in estimating fatalities or casualties, it is possible to define also the occupants of the buildings and at different times of the day. Because we know that usually, at least in Europe, if an earthquake happens during the night, this is usually the worst time because we have more people inside the residential buildings, which tend to be more fragile than, for instance, commercial and industrial buildings. Finally, the final three attributes, if you're interested in performing benefit cost analysis, it is also possible to establish how much does it cost to apply some of the retrofitting techniques. And for some insurance calculations, we can also establish some very simple limits and deductibles to estimate insured losses. So let me now take some time just to start overlapping this global exposure model with the global hazard model that I was telling you before. And this is just a simple case around Southeast Asia, once again, very high seismic hazard, but also very high exposure. And if you have a warm color, it means that the seismic hazard is quite high, and then the blue colors it means that it's quite low. And if you have a polygon which is quite high, it means that you have a large number of buildings. So for instance, in places like the Philippines or Indonesia, we have high seismic hazard and we also have a lot of buildings exposed. And for example, this type of results, it might not tell us a lot of information about the expected losses, economic or human losses. But for example, it allows us to understand the places in the world where we should dedicate some efforts, where we should probably try to have better information about soil conditions, perhaps do this type of campaigns in which we send people to the field and they collect building by building information, or where we try to have better damage data from past events. Let me see if this video will work. I noticed before that it's shaking a little bit. But basically we can see here across Southeast Asia, places where we have huge exposure. Okay, for instance, look at over there in China, around Shanghai or Beijing. The seismic hazard is not that high, but huge exposure. And then if you manage to see, for instance, the Himalaya belt, north of India, Nepal, and of course also Japan, huge hazard and also a very intensive exposure. This is another part of the world, now going from South America all the way to Alaska. It's also the subduction area around the Ring of Fire. And once again, in some places, we have the capitals of all these large countries very close to the subduction region, so high seismic hazard and also high exposure. Okay. A lot of the things that we do is also very specific. It's at the urban level, city level. A lot of the risk reduction interventions are at the city level, not at the national scale. So it's also important for us to try to understand what is the seismic hazard that is exposed to the different cities and the size of the cities. And this is in South Asia. But for instance, if we in this part here, we have the Balkan region and also the Middle East. We see here Belgrade, I believe, and Bucharest. And for instance, in these cases, we have cities with high population and still significant seismic hazard. So we look at a peak ground acceleration of around 0.15, at least in the current model, which again, it's a significant seismic hazard. So usually we connect the seismic exposure with the seismic hazard through what we call the vulnerability or the fragility component. It's basically the link between the shaking, the types of buildings that we have, and the expected losses. And in this case, it's different types of questions that we're trying to address. How was the damage, the loss, fatalities, and was the business interrupted? How much time do I still have? Can I have a watch? Okay, good. So in these cases, what we're trying to do, and I will go to the very basics here on the vulnerability modeling part. It's basically we know that with increasing seismic intensity, we know that we should expect increasing levels of damage in different buildings. This is just an example of different damage states. For example, for masonry, different damage levels for a reinforced concrete building, different damage levels for a wooden structure. Okay. So the relation between the seismic intensity, in this case, for example, peak ground acceleration, and the different damage states, it's basically what we call a fragility function. So you can see that for very high seismic intensity, peak ground acceleration in this case, we should expect 100% probability of having collapse. For something in between, for all the reasons I was mentioning before, like the building-to-building variability, record-to-record variability, the uncertainty that we have on the damage criteria, on the damage thresholds, we should expect basically different probabilities of having different damage states. If you're not interested in damage, but actually want to go directly to human losses, to economic losses, it is also possible to use what we usually call a vulnerability function, which establishes the relationship directly between different levels of shaking and directly what should be the loss ratio. Once again, because of all these uncertainties that we know that exist in the model, we can have not just a deterministic value for each level of shaking, but a probabilistic distribution, okay, which could follow different statistical models, and OpenQuake supports different statistical models. But you can see here that, for example, for 1G, for acceleration of 1G, I shouldn't have just a single value, but actually I could have a distribution of different loss values, each one with a different probability of occurrence. So again, since GEM was founded in 2009, there's been vulnerability functions for decades. So one of the things that we did, or that one of the global components of GEM did, was to go into the literature and try to collect all the fragility functions, all the vulnerability functions from different publications, and try to put everything in an online platform. So this is once again available online. You can go there. For instance, in this specific case, I just searched for functions which would be applicable to Italy. I'm highlighting over there the taxonomy. Okay, that code that was over there, it's basically, it was constructed following the GEM taxonomy, which was telling me that it's a reinforced concrete building with a given number of stories, and it was telling me information about the expected level of ductility. I can see a lot of information about the fragility functions. I can basically start adding them to my cart, because in my building portfolio, I might have different building classes. And then once I have collected all my different fragility functions, I can download my set of models, and they will be downloaded already in the format which is compatible with the OpenQuake engine. Okay. I don't want to make this look like it is extremely simple, because it is not. Okay, this is a useful resource. It's the OpenQuake platform is accessed hundreds of times per month by various people around the world, but it obviously requires a lot of engineering knowledge to understand if you are selecting the right fragility functions. A lot of times we have different intensity measures. We have different damage states, which a lot of times have to be harmonized. We also have to understand if, for instance, in this case, we have an LS3. So what is limit state 3? Is it actually structural collapse? It is complete damage? Is it near collapse? Is it near? Is it immediate occupancy? So it does require a lot of knowledge to understand what do the different damage states mean, and is this in agreement with what I want in the end? The development of this fragility function, of these vulnerability functions, can follow different approaches. There's literally probably hundreds of approaches to develop vulnerability and fragility functions. Probably one of the simplest one, and there's very famous studies in the 70s, was expert opinion. Basically, again, there's various methodologies, but in a very simplistic manner, a lot of structural engineers would be put in the same room, and then you would ask them, what is the level of shaking that I should expect 50% of my buildings to have slight damage? And what is the level of shaking that I should expect 50% of my buildings to collapse? Okay. Let's say all the different engineers, the different experts would provide their opinion, and then based on the collection of responses, a fragility function would be built. Okay. Different methods also weigh the opinions of the different engineers differently. Okay. We could basically follow this approach in which all the opinions are the same, or in some cases, a very brief questionnaire is given to the engineers up front, and then based on their responses. For instance, if they say, I'm very confident about my response for masonry because I've been working with masonry for many, many years. Or it could be, I'm not that experienced with this type of construction, so please don't take my answer as accurate. And in this way, basically, the responses from the different engineers are weighted. Then, of course, when we start collecting more and more information, for instance, in the 80s in Italy, there's a lot of information that has been collected in California as well. It started allowing people to develop empirical fragility function. So basically, what we do in this particular case is people go into the field after an earthquake, they collect the number of buildings in different damage states at different locations, and then by relating the number of buildings in different damage states with the shaking that was observed or measured, a fragility function can be built. In this particular case, you can see that actually there's a fantastic correlation between the data points that you see on this plot and fragility function. This is very rare, and I can tell you that in order to have this, I have to handpick the locations and the damage state and the number of buildings in order to build something like that. Empirical functions usually have a huge uncertainty for various reasons. For example, if you send 10 people into the field to classify exactly the same building, it is possible that you will have different answers. Some people might think that the building has extensive damage, others might say moderate, and some people might say the building actually has to be demolished, so I'm going to say that it's complete damage. Another huge source of uncertainty is the ground shaking. In some places like Taiwan, in Japan, California, even in parts of Italy, because the seismic station network is very dense, there's not that much uncertainty on the estimation of the shaking at the location of the different buildings. But in other parts of the world, there's not that many seismic stations, so then we basically have to use either reports of damage, okay, if you want to develop some fragility functions in terms of macroseismic intensity, or you will have to use ground motion prediction equations, which have a huge uncertainty. And in that case, we don't know exactly if this point should be here or should it be after, should it be a little bit towards the right, and because of that we have huge uncertainty in empirical models. Obviously, with the improvement of tools, improvement of also shaking table tests and experimental results, there's been a huge effort in developing better models, complex models, numerical models, which offer a lot of advantages. For example, you can control specifically the building classes that you are introducing in your model. You can control the strength of the concrete, of the steel, of the masonry, of course. And I guess more importantly, you can also control exactly the ground shaking that is going to be applied to the building. So in those cases, of course, we can have very complex models. I can now also take into account all these different aspects, like for instance, irregularities. You can see that this is a building located in the north of Portugal, and there's the owner decided that he needed to have a store, so why not move a column to this side? And this is the first part of the building that collapsed. So it allows us to take into account all these different attributes, from irregularities, from different types of construction, different design regulations, okay, and also different ground motion records which can be selected, taking into account the seismicity of the different regions. But of course, there's also a lot of limitations with numerical models. For example, we know that a lot of times the numerical models, for instance, the hysteresis models that we use for the different materials cannot represent exactly what we observed in past events, or for instance, cannot model exactly what we observed in shaking table tests. So there's also a lot of limitations in numerical models. And I think ultimately what it's good is to have a stable and comprehensive numerical model which can be validated with empirical and experimental data. Generally, there's a lot of guidelines. This was heavily led by the University of Colorado in the United States and also University College of London. And there's a lot of guidelines about how to process empirical data, analytical data, vulnerability functions for non-structural components. This is all available online. And I think it does provide very important guidance about what's the most appropriate methodology depending on the end use. This is also something that I just wanted to share about some of the applications of these methodologies. And this is actually a collaboration between Jen, between Svetlana and a student of mine that was from Nepal. And this is how we can sometimes try to use empirical data, damage data, and comprehensive numerical models. So for this particular case, Svetlana and a colleague of Svetlana in Nepal, they went after the event, they collected building by building information, detailed information about the drawings of the building, and we also have the damage patterns in a lot of the buildings. And with that, we basically managed to build several numerical models, each one of them with different limitations, to try to understand why the same building class, which was subjected to basically the same ground shaking because they were relatively close, some of them were presenting a lot of damage and others were not presenting damage at all. And in that particular case, it was because of the masonry density, okay? Basically, the density of the walls that we have in each floor of the building. And this was quite interesting because I was mentioning before that this type of models can also help people to improve the design regulations. And for this particular case, we noticed that there was not very clear or sufficient recommendations for the density of the masonry walls and the Nepalese code, and by understanding some of these results, both numerical and empirical, we were able to provide some recommendations about what would be the optimal wall density in order to make sure that the buildings have a better performance. Using a lot of these guidelines, a lot of these tools, because again, just like there's open quick to estimate risk, we also have developed what we call the risk models toolkit. It's just a suite of tools which can also help people to develop vulnerability functions. We have been developing hundreds of vulnerability models around the world. This is the case for the country of Colombia. We went through the process of collecting all of the existing fragility functions for Colombia, and we noticed that this was only, I think, covering maybe half of the building classes. There's actually a lot of good research, very good scientists in Colombia, but we wanted to make sure we had a uniform set of fragility functions. We didn't want the results to be biased because a different methodology was used. So 57 building classes, fragility functions for 57 building classes were developed. This type of, when we are developing these fragility functions, there's very different levels of complexity. I was showing you before that you can go to a 3D model in which we take into account all the particularities of the building, or instead, you can use something a little bit more simplified. Like for instance, single query freedom systems, okay? We can still cross it with several ground motion records and use dynamic analysis, but as you can imagine, a single query freedom system runs in a fraction of a second, while a 3D model takes a lot of time. But sometimes we cannot escape doing the complex models. And for instance, for the particular case of Costa Rica, there were some building classes that we thought initially they were quite simple, but we really needed to do some proper structural modeling in order to take into account some specific failure mechanisms in some of these buildings. For instance, for this particular case, the country has a very comprehensive social program that we're basically giving buildings to people with low income, and they use this combination of concrete panels with steel beams, and this was not being captured in the simplified model, so we had to develop these complex 3D models to properly account for the vulnerability. So when we start now combining the seismic hazard, the exposure, the vulnerability, now we can start calculating earthquake losses, damage, probabilistic risk. We do this through the OpenQuake engine, and we're going to have a presentation much better than what I'm going to show here after the coffee break from Venezia about what OpenQuake can do and not do. But I will provide already some information. It's free, publicly available, it's open source, which means that if you do not like the methodologies which are there, it is possible for you to change them and even propose your own methodology so other people in different countries can use it. It does both scenario and probabilistic risk. Okay, so if you're interested just in a single event, it could be a past event, you can use it. But if on the other hand, you want to calculate losses considering all the possible ruptures, all the possible earthquakes that can happen in your country, it is also possible. It does hazard and risk, okay? So I know that other tools out there, they basically estimate hazard and then you have to bring another tool to estimate risk. This one, you can do just in a single run, both hazard and risk calculations. You can use it for single building risk analysis, okay, or just at the city level, urban level, or you can also do it at the continental scale, as is the case with a SERA project. It considers a wide spectrum of uncertainties, mainly on the seismic hazard. You can have different seismic zonations, different source models, which is the case, for instance, of SHARE, which had 3 main source models. But you can also take into account different ground motion prediction equations. So deep epistemic uncertainties can be very large. And then we also have a lot of aleatory uncertainties on the vulnerability. If you remember, I was showing that plot that for a given level of shaking, you don't have just one value of loss ratio, you have a probabilistic distribution, so all of this can be propagated. And finally, for relatively small calculations, you can run it just in a single laptop. If you want to run very intense calculations at the continental or national scale, depending on the size of the country, you can also install this in a cloud or, for instance, in a large server. So starting from the basics, we can basically just replicate past events. And OpenQuake is compatible with the very well-known USGS shake maps. I think you've all seen shake maps every time there's a destructive event. The page group from USGS, they release right away this PDFs, it's just one page, which provides really important information about where should we expect higher shaking, where should we expect the damage in the different places. And what you see here on the left, it's precisely a shake map from the USGS. And in OpenQuake, it's compatible, so it's capable of grabbing this shake map which exists online. It grabs the shaking from the shake map, and then it grabs your exposure model, your vulnerability, and estimates losses and damage. This is, for instance, a repetition of the 1999 Armenian earthquake in Colombia. You can see what was calculated and what was observed. A more recent event in 2016, the Muisne earthquake in Ecuador. Once again, we grabbed the shake map from the USGS and we used the exposure and vulnerability that was developed within a previous regional program. And in a matter of a couple of hours, we estimated the number of collapses on the different municipalities in Ecuador. I'm using this example here for another reason. I was mentioning before that if you have a huge uncertainty on the ground shaking, you will also have a huge uncertainty on the risk, and this was actually the case of Ecuador. Despite the fact that Ecuador does have a lot of seismic stations in different parts of the country, they were not available to basically constrain the shaking from the shake map. So the uncertainty in this particular analysis was very large. But we can also replicate events that either they are historical, they happened, but they happened more than 100 years ago. So there were no measurements, there was no recording stations, we don't know exactly how much was the shaking in the different places. Or for instance, hypothetical events. Basically, you know that you have an active fault in your country, you know that this fault can generate, for instance, a magnitude 6 or 7, and you want to, basically, it's the what-if scenarios. And in this particular case, this is a repetition of the historical event in San Francisco. It's a magnitude 7.6, if I'm not mistaken. We have the epicenter here. This is just one realization of the possible shaking across the region, okay? This is the losses now, okay? So I grab the shaking, I check how much was the ground shaking at the location of the different buildings or the different, this is at the census tract level. I use the different vulnerability functions for the different building classes and estimated losses, and this is the sum of the losses on the different places. I also want to share with you just a few slides of, for instance, how does it look running some of the calculations in OpenQuake. So OpenQuake is compatible with this QGIS tool. Maybe some of you have used ArcGIS, which is basically the commercial version of QGIS. QGIS is just a simple tool that allows you to do maps, to download data sets, and basically to come up with a visual representation of how much were the losses. I was in Nepal a month ago, and in Nepal we were discussing a lot about earthquake risk and earthquake hazard. And for this particular case, this is the shake map, once again, from the Gorka earthquake that happened a few years ago. Okay, this is the shaking across the country. And this was the estimated losses. Okay, Vitor will show a few examples about this as well for Greece. But again, it's very easy to run, it's very easy to start visualizing some of the results. And QGIS is also open source, which means that if you want to bring data sets for your country for the road system or the bridges or some satellite data on the top, basically all of this is quite compatible. But what about a probabilistic risk? So not considering just a single event, but for instance going through this probabilistic seismic hazard models that I was telling you before and start generating what we call a stochastic event set. So a stochastic event set is basically a possible realization of the seismicity that we might have in a given year. Okay, I could grab, for instance, the seismic hazard model for Serbia, okay, and I could generate what could be 1 year of seismicity. Maybe there's no earthquakes at all, but maybe there will be a magnitude 5 or a magnitude 6. And I repeat this again and again and again and again. What we're trying to do is basically, if you could get on the time machine and check where and how are going to be the earthquakes in the next 10,000 years, for instance, in the Balkans. And this is what these probabilistic seismic asset models are doing. They are generating possible realizations of seismicity, okay? For this particular case, I'm showing an example at the global level. So I use the global mosaic of seismic hazard models that I presented previously, and I start generating many 1 years of events. Okay, you can see that in a lot of places of lower seismicity, there's no events, but then from time to time, something is generated. And then if you look around the Pacific Rim, okay, and in some places from the Balkans, the Middle East, the Himalaya, we do have events, perhaps of small magnitude, but they happen almost every year. Now, let's just go step by step. So, in showing you an example for Costa Rica. For instance, let's say that I grab a big event. 5 minutes, okay. So I just produced a huge stochastic event set for Costa Rica. One of the events was a magnitude 8.1 subduction, okay. OpenQuake always models the ruptures as a plane or as a complex fault, but basically it's never just a point source, okay. There's always, it models always the geometry there. For this particular event, I can start generating how much should be the shaking. You can see here that basically there's different possibilities of the ground shaking for the same magnitude, because we know there is a huge uncertainty here, right? If you have a magnitude 7 occurring, for instance, in Japan, and magnitude 7 occurring in Costa Rica, we do know that the shaking will be quite different. There's huge uncertainty on estimating of the acceleration on the different places. It's what we call the aleatory uncertainty, and also epistemic uncertainty, because we can have different ground motion prediction equations being considered. But this is all propagated within the risk analysis, okay? And for instance, in this case, this is the mean shaking for this event of magnitude 8.1 in Costa Rica. I can now bring the exposure, okay? And for the particular case, Costa Rica is it's a very unique case, because it's a country with 4 million people, but the huge portion of the population is concentrated just in a single location. This is the metropolitan area of San Jose, the capital, okay? So I had the shaking, I have the exposure, now I bring all my vulnerability functions, and I think we have about 50 different building classes in Costa Rica, and I can estimate what would be the economic losses across the country. This is done for a single event, okay? But if I generate, for instance, 100,000 years of events in Costa Rica, I'm going to have thousands of events. So I go to my next event, now magnitude 7.1, located on a different location. I have the shaking, and I have the earthquake losses once again. Once again, now magnitude 6.5. Interesting enough, for instance, for Costa Rica, one of the worst cases that could happen, it's not necessarily this huge magnitude 8, in the subduction area, but it's actually shallow events, still of moderate magnitude, very close to the capital, okay? In this case, we have huge losses around the capital of San Jose. I can repeat this many times, okay? If I have 20,000 years of events, let's say that in 20,000 years, I generate 1,000 events. I can sum the losses from all of these events, and I can divide by 20,000, okay, because this is the amount of years that I have used in the generation of my losses, and I get what is usually termed as the average annualized losses, okay. This is exactly what I'm showing here for South America. So for each one of these countries, I have generated a lot of events for a given time span. Then I basically estimated, okay, I understand that I can have 10 billion euros of losses for the next 10,000 years. But if I divide that by the 10,000, I get my average of the losses. It's not saying that every year we're going to have losses, not at all. We can have many years where there's absolutely no losses due to earthquakes. But basically, eventually an event happens and it's a very high loss, and we're just distributing these very high losses across the different years. We can also have what we call probable maximum losses or loss incidence curves. Many names are given to these curves. In this particular case, what we're checking is how many times different levels of losses are exceeded, okay? Well, obviously we know that very high losses are only exceeded for very large time spans, and of course low losses are much more frequent. Another good thing is using the same methodology for the exposure, for the vulnerability, for the seismic hazard, for the calculation of risk, is that it's fair now for me to compare the different countries, because I know that I have reduced the bias of using different methodologies, and it's easier for me to compare now the risk between the different countries. This process has been repeated for all the countries around the world, and this was released in December 2018, and we have produced for the first time a global seismic risk map. So basically what you see here is the normalized losses across the world, and you can see that, for instance, for the Balkans, almost for all the countries there is a significant seismic risk. Of course, now you can start understanding where are the losses coming from. So we know that most of the losses come, for instance, from countries like Japan, China, United States, Turkey, because it's countries with a lot of population, a lot of buildings, a lot of capital stock, very significant seismic hazard. And in some cases, like for instance in China, in Turkey, there's still high seismic vulnerability because of some of the older construction. Okay, this is just some normalized losses. We can also start bringing all these pieces together and start building what I mentioned before, this profile, this country profile, which is basically just in one page, give me everything that I need to know about seismic hazard, about social vulnerability, about exposure, about risk for the country. This is just an example for Portugal, but you can find already a few examples online. I think I will not go in detail in here because I think you will cover some of this, Helen. Or less. But basically, a lot of these country profiles are already available online. They will be heavily updated, okay? And I can tell you for the specific case of Europe, they will be completely replaced next year once the new SERA model is released, because we know there's a lot of limitations with this first version, so everything is going to be updated. But what we have here is basically some social and risk indicators, past major earthquakes, the expected average annual losses for residential, commercial, and industrial, and some interesting information about the population and the economy of the country. Seismic Asset Maps, which is one of the basic data sets, and risk modeling, also the risk normalized by the cost of the buildings on the different countries and so on. Okay. This is also something that we have released. It's basically, it's a poster, it's a map, which includes not just the seismic risk, but also the seismic hazard exposure and also fatalities. All of this is available on the OpenQuick platform, also on the GEM website, so you can go right there, right now, and download all this information. Finally, we've been doing just some work on validation of the models. And basically, in this particular case, what we're doing is just comparing the losses that this model is generating, okay, take into account the magnitude, the location, and the shaking and past events, okay, and then comparing with how was the number of collapsed buildings and economic losses and so on. Okay, so this particular case is for economic losses, yes. And here it's basically comparing this metric that I was telling you about, the average annual losses, with other studies that existed in the past, like for instance the Global Assessment Report from the United Nations, and see if we have a trend, if there are some similarities, or in some places we are heavily underestimating or overestimating the losses. And if that's so, we basically take a step back and we revise the different components of the model to try to understand what are the reasons for that. Okay, this is my last slide actually. I just want to say that also one of the best ways for us to try to validate the models, to improve the model, is to do events like the one that we have here, in which basically we come, we discuss risk, we discuss vulnerability, we check the exposure models, we find limitations, and we also try to find solutions. This is all the places where we've been doing this type of scenarios, this type of events, this type of workshops around the world. I was also very happy to have the support from Svetlana. We were together a month ago in India, correct, Svetlana? Maybe a little bit more than that, in Gadinagar, doing something like this with different people. India is basically it's a country, but in fairness, it could actually be a collection of countries, right? So we have different representatives from different parts of India. It was extremely interesting. I was 1 month ago also in Bandung, in Indonesia, having a similar workshop with people from the Philippines, from Papua New Guinea and Indonesia, of course, having these conversations. And I'm very happy that for my next presentations, I will be able to say that Belgrade is also now part of this list. So with this, I just want to thank you once again for coming here. I'm very happy to see some people that we've been exchanging emails, the colleagues from Croatia, from Slovenia, so it's very happy for me to be here, and I hope that this will become a tradition, that in 2 years it will be somewhere else, but we will continue seeing this happening. Thank you.